Dear students of class 11th, अस्सलाम वालेकुम रहमतुल्लाहि व बरकातहू। जैसा कि आप जानते हैं, हम स्टेट्स ऑफ मैटर डिस्कस कर रहे हैं, जो हमारा नया यूनिट है। इसमें हमने देख लिया कि जो मैटर है हमारी सराउंडिंग में अवेलेबल, इट एग्जिस्ट्स इन 3 फिजिकल स्टेट्स, दैट इज सॉलिड, लिक्विड एंड गैस. Though there are 2 other states, plasma and Bose-Einstein condensate, but they are not present in our surroundings. So we discuss only about the 3 states which we come across in our daily life. So the basic difference between these 3 states of matter is that the variation exists there in the intermolecular force of attraction between them. In solids, the force of attraction are very strong. In gases, the intermolecular forces are the weakest, whereas in case of liquids, these intermolecular forces of attraction are intermediate between solids and liquids. Yesterday, we discussed the different types of intermolecular forces, and we find that there are some 6 types of intermolecular force of attraction. One of them is called as dipole-dipole interaction. Second one is ion dipole interaction. Third one is ion induced dipole interaction. And the fourth one is dipole induced dipole interaction. Fourth one is London or dispersion forces. And the sixth one is hydrogen bonding. So far we have discussed the first 3 types of intermolecular forces, that is dipole-dipole interaction, ion dipole interaction, and ion induced dipole interaction. Today we are going to discuss the 4th type of intermolecular force, that is dipole induced dipole interaction. This is the 4th type, dipole induced dipole interaction. Very easy to understand. The name indicates dipole induced dipole interaction. It means simply when a polar molecule having a dipole approaches a non-polar molecule and this polar molecule induces polarity in the non-polar molecule, then the force of attraction existing between these 2 polar and non-polar molecules will be termed as dipole induced dipole interaction. So this force of attraction which exists between a polar molecule, that means this polar molecule has already a dipole in it, and when it approaches, attraction which exists between a dipole molecule, polar molecule, and a non-polar molecule in its surroundings or in its neighborhood. This force of attraction is called as dipole induced dipole. Let there is a molecule AB molecule. This is a polar molecule, so B will have a negative charge on it and A will have a positive charge on it, or we may say B will have positive or A will have negative. That will depend upon the electronegativity difference of A and B. If there is a molecule like helium in its neighborhood, this helium has its own electron cloud. So what will happen? During orientation, the positive part of this polar molecule, suppose A positive, it will direct itself towards helium, and this positive part of A, it will attract the electron cloud of this helium in this way. that is electron cloud of helium will be attracted towards this polar molecule. As a result, partial negative charge will develop on this part of helium and partial positive charge on this part. So the attractive force will now operate between this AB and a neutral helium molecule. This force of attraction is called as dipole induced dipole interaction, and it is also called as induction effect. Whenever this type of attraction exists between the molecules, it is called as induction effect, and this type of force, existence of these forces, were studied by Debye. So this is another type of force of attraction. Naturally, this is comparatively a weaker force of attraction. Then there is another type of force of attraction which we call London forces or dispersion forces. This is the fifth type of force. Fifth type of intermolecular force is called as London forces or dispersion forces. London forces or dispersion forces of attraction. Now, one thing is very important. So far, we have observed that in the above four types of force of attraction, either both the molecules or one of the molecules has a charge on it, whether a permanent charge or some partial charge. So in dipole-dipole interaction, we observe that both the molecules are polar in nature. The positive part of one attracts negative part of another. In ion dipole interaction, there once again one molecule has complete positive charge, one species has complete positive charge, and another one has partial positive charge. That means there again attraction exists between these charged particles. In case of ion induced dipole, once again this attraction takes place only when one of the molecules or one of the particles is having charge on it. And in case of dipole-dipole interaction, dipole-induced dipole interaction, once again, one of the two particles is polar in nature. But as per this London or dispersion force is concerned, so in all the four cases, one or both the particles where force of attraction exists, one of them is at least polar in nature. But in case of London or dispersion forces, these forces exist in molecules like O2, N2, H2, Cl2, and the same way in helium, neon, argon. These are the molecules which are non-polar. So the force of attraction existing between these non-polar molecules, especially in their liquid and solid states. Liquid and solid states. There exists when these molecules are present in liquid state or in solid state. Since they are non-polar, there doesn't exist any sort of polarity on them, but there must be some force of attraction when they exist in their liquid states or solid states. What is the nature of the force which exists between these non-polar molecules in their solid and liquid states is called as dispersion or London forces. This force is called London forces because these forces were discovered for the first time by Fritz London in 1970. Fritz London in 1970. This is why these forces are called as London forces. So how these forces begin to operate in these non-polar molecules? It is suggested that these molecules, which are neutral molecules, which didn't possess any charge on them, but since they are having an electron cloud available in them, electrons are present in these molecules. These electrons are continuously moving around the nuclei of the atoms, around the nuclei of the molecules. So electrons, when they move from one part of the atom to another part, then a sort of instantaneous dipole is created. In these atoms or molecules, what happens? Instantaneous dipoles are created by the moment of momentary motion or by the momentary motion of electrons. For example, let's take the example of helium. This is helium atom. This is the electron cloud around the helium. There is another helium and it is surrounding that will be having same type of electron cloud. But when these London forces begin to operate, and then what happens actually, this electron cloud, when it moves around the atom, it goes to one side. For example, this is nucleus. The electron cloud goes to this side during its motion. So that means this part of the atom becomes negatively charged and this part becomes positively charged. So this atom in its neighborhood, it will now attract the electron cloud of another helium atom towards it. That means that helium will also develop a negative charge on its one end and a positive charge on its another end. But this dipole which has been created here, it is called as instantaneous dipole, or it is also called as momentary dipole. It is because this dipole has resulted, it came into existence by the movement of electrons. Since electrons are continuously moving, they won't remain permanently in this very state. They will move to other side of the atom very quickly. This is why these dipoles are not permanent dipoles. This is why they are called as instantaneous dipoles. So these instantaneous dipoles are actually responsible for the attraction of these neutral molecules in the solid state and liquid state. This is why this type of force is called as this type of force is the weakest force, and they are called as London or dispersion forces. So in this type of force, it comes into existence by the creation of dipoles for a very short period of time. And these dipoles which are created, or these forces which we call London forces or dispersion forces, their magnitude depends on two important factors. Two important factors are there on which the magnitude of London forces depend. One of the factors is size or complexity of the molecule. Size of the molecule, or you may say complexity of the molecule. That means if the molecule is larger in size, it's a simple thing to understand. If the size of the molecule, if molecule or atom is larger in size, that means electron cloud is larger in size. There is a big electron cloud revolving around the atom. So when there is a big electron cloud, this big electron cloud is easily affected by the nearest polar atom, nearest polar molecule. If there is another molecule in this neighborhood, if due to moment of the electron, the dipole got created in that molecular atom, and the other atom in its neighborhood, if having a larger electron cloud, will get easily polarized by the previously created dipole of the molecule. So the electron cloud gets easily distorted, it gets easily polarized by the neighboring polar molecule. So if the size of the molecule is larger, that means electron cloud is larger, that means this dipole will be easily created. This can be understood by taking the example of methane SiH4, then there is Celian methane CH4, then there is Celian SiH4, then there is germane GeH4. We know that carbon, silicon, and germanium, they belong to the same group of the periodic table, and this is why they resulted in the formation of the same type of hydride, CH4, SiH4, and GeH4. Both all the three molecules are neutral molecules, but still we observe that in these molecules the boiling point differs. Methane has a boiling point of 112 Kelvin, Celian has a boiling point of 161 Kelvin, whereas germane has a boiling point of 183 Kelvin. So this difference in the boiling points of these molecules indicate that there are different forces of attraction. In germane, the force of attraction are stronger than Celian, which in turn are stronger than methane. So stronger force of attraction resulted into higher boiling points. and higher boiling points. So it indicates that here the forces, since they are neutral molecules, the forces in them will be dispersion force or London forces, but the magnitude of these London forces differs. It is because the size of the molecules differs. Germane, it is a larger molecule, larger in size, while as selene it is smaller and methane is still smaller. So the size of the molecule has a prominent effect on the London or dispersion forces. Then there is another, you can also observe this type of difference in case of noble gases: helium, neon, argon, krypton. Since they are neutral atoms, you will observe that here the boiling point increases as we move downwards. It is simply because the size of the atoms increases on moving downwards. That means size of electron cloud increases, which results in the increase in the dispersion magnitude of dispersion forces. So this was one factor, that the size of the molecule. Since this size of the molecule, in other words, you may see that if you will move down the group, the atomic mass of or molecular mass of the compound also goes on increasing. So increase in molecular mass results in the increase in the London or dispersion forces, and because of that, increase in boiling point takes place. Then there is another factor on which this London force depends, that is the geometry of the molecule. Geometry, or which we call shape of the molecule. Shape of the molecule plays an important role in deciding the magnitude of the London forces or dispersion forces. Let's take a simple example to understand the effect of geometry or shape of the molecule on the London or dispersion forces. We have a compound C5H12, which we call pentane. In general, we call pentane. This pentane has three isomers. Let's take its two isomers. One of its isomers is normal pentane, CH3, CH2, CH2, and CH3. CH2 and CH3. This is pentane. 1, 2, 3, 4, and 5 atoms. This is normal pentane. Then let's take it as neopentane. Neopentane has the structural formula like this: C, CH3, CH3, CH3. That means all the four carbon atoms are attached to one centrally located carbon atom. This is neopentane. Neopentane. Now you see, this normal pentane, it's actually a zigzag type of molecule having this type of shape. This is the shape of neopentane, it's normal pentane. If there is another normal pentane molecule in its neighborhood, this will be the shape of that neighborhood molecule. So you see, in this molecule, this is the shape. Now this is neopentane. You see the shape of the neopentane. You see, it is a spherical molecule, this type of molecule. It is spherical. So another neopentane molecule which will be in its neighborhood, that will be of this type. That will be again a spherical molecule. Now you can observe that in case of normal pentane, there is a large area which is in contact with each other, whereas in case of neopentane, there is only a small area in contact with each other. Since these London forces or dispersion forces depend upon the size of the electron cloud, so in case of neopentane, only a small portion of the electron cloud is in contact with each other, whereas in case of normal pentane, a large portion of the electron clouds are in contact with each other. With the result, in case of this normal pentane, there are maximum sites of force of attraction, and because of that, the dispersion forces or London forces in this case will be stronger, while in case of neopentane, since there is a small portion of the molecule in contact with each other, that means small electron cloud portion, with the result the force of attraction here will be weaker, and naturally the boiling point of neopentane will be higher than that of normal pentane will be higher than that of neopentane. It is simply because the shapes of the molecules has its effect on it. You can see that boiling point in case of normal pentane is 36.2 2 degrees Celsius, whereas in case of neopentane it is 9.5 degrees Celsius. Now you see the difference between the boiling points of these two compounds, though they are having same molecular formula C5H12, and hence they will have the same molecular mass. So here the difference in the boiling points is because of the shapes and structure and geometry of the molecule, not because of the difference in their boiling points, in their molecular masses, because they have same molecular formula, so the same molecular mass. So if there is difference, that is because of the structure. So this structure or geometry of the molecule, it plays an important role in deciding the nature of the London or dispersion forces. So this is the fifth type of force. The sixth one is hydrogen bonding, and you already know that we have discussed hydrogen bonding in the previous chapter, chemical bonding, in detail, so there is no need to discuss that once again here. So this is the different types of forces which are generally present in case of different states of matter. Different now 6 types of force of attraction you have come across. These forces decide the physical properties of the solids, liquids, and gases. So with this we concluded the different types of intermolecular force of attraction in the 3 states of matter, and tomorrow inshallah we will start the first state of matter, the gaseous state, then later on liquid state, and the solid state is generally discussed in 12th class. Here we discuss on these 2 states. So inshallah from tomorrow we will start with the gaseous state of matter. So for today it is all. Thank you very much.